Good afternoon, everyone. My name is Zach Sweigart, and I'm a staff Android engineer at Faire. And I'm going to chat a little bit about the work we've done over the last 6 months to improve the speed of our app. So today we'll cover the 5 main steps on our journey to improving our speed: define, measure, analyze, improve, and control. But first, I'll chat a little bit about Faire. Faire is an online wholesale marketplace where retailers can shop from local independent brands to stock their stores. And this allows small businesses to compete with big box chains. Our mission is to empower entrepreneurs around the world to chase their dreams. And our app provides a way for those retailers to connect with the local brands and shop for the right products for their store. We also help eliminate inventory risk by providing access to capital with really clear financial terms. So, jumping into speed. Say your manager comes to you and says, "I want you to improve the performance of our app." Your response will probably be, "What do you mean? Performance can mean a whole bunch of different things." And say they want the app to be fast. Well, that doesn't really help much either. Speed is a bit of an umbrella term that can refer to a whole bunch of different things, such as latency, which is the time delay between the cause and effect of some change being observed; responsiveness, which is the time delay between a user input and giving visual feedback; jank, which is the perceptible pause in smooth rendering or scrolling; or layout shift, which is the perceptible movement in UI elements after the initial load. For our purposes, we wanted to focus on latency. And we define this as the end-to-end time from user interaction until we produce an interactive UI. And so I'll be referring to this as latency, timed interaction, or TTI throughout the rest of this talk. So the next question you probably have is, why? Why do we want to improve the speed of our app? Your product managers probably have a whole bunch of feature ideas. You probably have some other tech debt you want to tackle. Why should we focus on speed? Say you open up the app and you get this wonderful experience. You see a loading screen, you sit there for a few seconds, nothing's really happening. You probably close the app, maybe reopen it, maybe you go to a competitor app, or maybe just give up and go about your day doing something else. Some research from AppsFlyer showed that 70% of mobile app users will abandon the app if it takes too long to load, and even a 1-second delay in response time can result in a 7% loss in conversion. Google did some research on the web, and they showed that for web pages, if the load time increased from 1 to 3 seconds, there was a 32% increase in bounce rate. And as a mobile user, I can tell you I'm a lot more impatient than that. When it comes to time, there are kind of 4 important limits to keep in mind. First is you've got 16.7 milliseconds to render your screen to maintain 60 frames per second. Next, at 100 milliseconds is the kind of limit for users feeling like they're directly manipulating the UI. So this is touching a button and seeing that ripple. You've got about 100 milliseconds. At about 1 second, users are still feeling like they're navigating freely throughout your app without having to wait. And 10 seconds is about as long as you can keep a user's attention on a single task. And when it comes to your app, you probably have sessions that are much longer than 10 seconds. But during that time, your users are performing multiple tasks. So for us, it's adding something to your cart or checking out. You got about 10 seconds. So when it comes to our app, we have a giant app with hundreds of thousands of lines of code, and we've got 20 developers. And we can't optimize speed everywhere, not all at once. So we defined a set of what we called critical user actions. And these are actions that are most common to the user's flow, and are correlated with how frequently they do them, how they fit into the core business proposition of our app, and how much they're correlated with our revenue. And so some of the things we identified are viewing a product, adding that to your cart, checking out. And now that we had those, we had to set some measurable goals. So first we set our app load time goal to be less than 2 seconds. And then for each one of those critical user actions, we defined aiming for less than 1 second, 95% of the time for each action. Now that we've got our goals identified, we have to measure them. We have to see where we're at and where we need to get to. So we decided to build a system to gather some data. Some of the goals around the system is we wanted to make it really easy for developers to measure TTI, to integrate this directly into the actions they cared about. So it wasn't a lot of work for everybody to add. We also wanted to make sure we could track the total TTI for the action, again, including that immediate user action all the way through the screen rendering. And finally, we had to handle the app lifecycle. If you open up one of our screens and it's starting to load and you background the app, we don't really care about that time that the app is in the background because you're not really paying attention to us. So for our app, most of the actions that we cared about result in some form of navigation, whether that's changing between fragments, showing a pop-up, which is usually a fragment, or navigating between activities. And so the user will take an action, we'll perform some navigation, and then we'll render that new screen. We have a centralized navigation performer that handles all the navigation throughout our app, and that's where we'll start the trace, and then we'll stop the trace as soon as the screen is drawn in an interactive state. Looking at our performance monitor, it's a really simple interface. You see we just have navigation initiated, which kicks things off, and screen is interacted, which kind of ends the trace, and we'll eventually track that to our servers. And then we also implement the default lifecycle observer, and this allows us to override onStop to mark a trace as interrupted. We actually still track all of those instances where the user would background the app and kind of wait for a while to come back, but this allows us to exclude them from our analysis later on. And then when we create our performance monitor, you can see we pass in the process lifecycle owner. So that means that onStop is for the entire process when the app gets backgrounded. Next, in our navigation performer, you just pass in a simple navigation request, and the performance monitor kicks things off. And for developers, when they're creating these navigation requests, all they had to do was override this should report value with the name of their screen. And here you can see it's the home screen. That's essentially a sealed class that has these various objects that have an identifier, so a home screen identifier. And by default, it's turned off. So we've got a whole bunch of probably 100 different screens within our app, and most of them are set to off, and we started with those 12 key actions. So now that we have the trace being started, we have to wait till we render the screen to stop the trace. In our app, every state for rendering a screen is a UI state, and we have kind of this sealed class that has our loading state and then our content ready. And that content ready allows us to mark a screen as interactive or non-interactive. Our screens are built with Jetpack Compose, and so we subscribe to the state and start with an initial loading state. And this allows us to maintain that responsiveness. So user performs an action, we open up a new screen as fast as possible under that 100 milliseconds and start with a loading UI. And while that's happening, we'll be processing data in the background. Once that content is ready, if the UI state is interactive, we use a launched effect to mark the screen as interactive as soon as we're done drawing. And if you haven't used launched effect, it's a way to use side effects that are outside the scope of the composable function. So this will launch a block into the compositions coroutine context, and this only gets relaunched when the view is recomposed with a different key. So if we go back to this, you'll see we're using this screen as our key, and that screen is actually the top level composable, so it will only run when the composition is done on the very first time. Then for handling the onDraw, we just plug into the view tree observer, and onDraw we mark it as interactive and ready. So if you're using Jetpack Compose, you'll probably be familiar with this little diagram on the side. We'll do composition, layout, and then drawing is the very last step, and that's as close as we can get to when the screen is interactive for a user. So we put this out in the wild, we gather a whole bunch of data from end users, and you'll want to gather data from end users because running it on an emulator on your device on Wi-Fi is not really realistic to how users are going to be using your app. So from the raw numbers, we gathered that 8 of the 12 actions we cared about were only below 1 second 50% of the time on Android, and the iOS team was only for 4 of the actions, so there was a little bit of competition going on there. But it also noted that there's a lot of room for improvement on the client side. This wasn't just our back-end engineers that could fix this for us. And when it came to the P95 actual times, we were about twice as long on Android than iOS. So where does all this latency come from? Where are we being slow? First, to render a screen, we need to load some data, which possibly comes from the network. Maybe it's from disk or in some cache. Then we process that data. We build a UI state. And then finally, we draw the screen. Starting with loading the data. First, we want to look at our network. And if you have not used the network inspector, it's built right into Android Studio. You just go down to App Inspection. It used to be under Profiler, but I think it moved. And so this will show you every network request that your app is making. You can see different information on like how long the request took. If you click in, you can also see headers, response and request values. And on the timeline at the top, you can highlight that to kind of focus in on an area you care about. So maybe you click a button, and then you highlight in on all the requests that are happening after that. This is a screenshot from loading our brand detail screen, and there's a lot of network requests going on just to render our screen. 37 network requests to be exact, which was a little wild. One other thing that comes with mobile development that I'm sure you're all familiar with is a lot of our users aren't on Wi-Fi. They can be using the app from wherever they want, which is great. We wanted to figure out where our apps were being used. So we dug into the network type by adding some logging, and we found that 25% of our sessions were not on Wi-Fi. And for these sessions, it was really interesting. We did an aggregate of all the actions, and we found that 5G was actually about the same speed as Wi-Fi, which is pretty cool. 4G was about 15% slower, 3G was 80% slower, and then we have this other bucket, which was networks that weren't in the standard list of the telephony manager that's built into Android. So these were about 25% slower. The only thing we can say about these for sure is that they're not Wi-Fi, they're just some mobile network. And so you can see that outside of 5G, which was only 8% of our sessions, the rest of those cellular network sessions are going to take additional time just over the wire. So now we've looked at the networking time, so let's take a look at the next step, which is client processing. We use RX heavily throughout our app. If you've moved on to Flow or are using another streaming system, this may not be completely exactly what you're doing, but the general principles will probably apply. So in RX, for our screens, we generally combine a whole bunch of data streams that come from all over the app. Some of them are coming from network, some of them are coming from cache or computed values, and we use this observable combine latest. And the interesting thing to note about this is that it won't emit a UI state until every single one of those streams has emitted at least once. And you'll see at the bottom, I didn't even show all the streams here because for our product screen, we were combining 21 data streams. And so we had to figure out which one of those was on the critical path, which one of those streams were slowing us down. Looking at just the network and client processing time, that was 95%, more than 95% of our latency that we were measuring. So we actually didn't really dig into building our UI state or Jetpack Compose rendering too much because we had a lot of low-hanging fruit to tackle already. Okay, so we found where the slowdowns are. We now want to make some improvements and speed up our app. Some of the main principles we started focusing on were whenever you're trying to improve speed, you want to eliminate duplicate work, wasted work, unnecessarily serial work, or any non-blocking work that is blocking. In kind of a more strategic approach, we wanted to first optimize our network use, unblock the screen as early as possible, and cache and prefetch data. Starting with optimizing network use. Going back to this screenshot from our brand detail screen, you can see this red line connects the first network request to that one further down, and the one further down doesn't start until that one at the top finishes. Along that line, there are about 5 network requests happening in parallel. And we use OK HTTP for our network layer. And if you dig into the OK HTTP dispatcher, you'll find these 2 variables. There's max requests and max requests per host. Whenever you make a request, it goes to the dispatcher, which puts it into a queue. And if the queue has room, it'll call this promote and execute function. First, it'll check if there are more than the max requests concurrently happening, and that's across any request that your app is making, whether it's your app or if you're reusing it for analytics or anything like that. And if it's less than that, then it will check this max requests per host. So it'll check on a per host basis. So this is default set to 64 max requests parallel at a time and 5 per host. You can really easily override this. When you create your dispatcher, you can set it to, we set it here to 10, and then when you build your OK HTTP client, you can just pass in your new dispatcher. Just making that one line change now, you can see all of these extra network requests running in parallel. And doing this, we found that as an aggregate across all 12 actions, we saw a 25% increase in the number of actions that were happening less than 1 second. So a huge win with just a single line change. And you might be asking, okay, so we set it to 10. Why don't we set it to 20, 40? We can keep going. There's a little bit of a drawback to continuing to do this, and it's more of a Band-Aid fix than a long-term fix. You have to worry about overloading your server. If you are sending 64 connections at a time to your server, you might have your server thinking that you're trying to DDoS them, and then your user is blocked. You also have to worry about starving different hosts. So if your analytics are on a separate host than your main application, and that is using up all 64 network requests, your critical request won't go through until at least one of those analytics completes. So you don't really have a lot of control over the priority there. It'll just eat up all your connections. The other thing we found when we started looking through our app is we had some diminishing returns on most screens. So the brand screen is particularly bad with 37 network requests, but for a screen that only needs 2, if you set this to 10, it doesn't make any difference at all. So we experimented with this, and we found that 10 was a good balance between the traffic that was going to our servers as well as the performance gains we were getting. The other thing to look at that we started to look at with optimizing our network use were to deduplicate network requests. For the brand screen, several times we were calling our get brand endpoint. And to do this, we just used a repository that kept track of network requests that were in flight and then just don't make those requests again. We also moved our analytics to a separate host. So like I mentioned, if it's on a separate host, it's using a separate batch of those connections. So we can have 10 connections going to our analytics and 10 connections going to the services that we actually care about getting data from. Doing this, we reduced that 37 network calls to 18, which is like a 50% reduction. We still have a long way to go, and I think there's some API redesign that we can do to bring this down even further, but this made a huge improvement on our performance. Next, we'll look at unblocking the screen. So a common pattern to unblock your screen early is lazy loading, and you may be familiar with this if you've got an infinitely scrolling list and you're paginating data. You're lazily loading elements further down the list. But you can lazy load pretty much anything on the screen. On the left, you can see in this screenshot, when we open up the screen, everything kind of renders in all at once. Where on the right, you can see that 200 minimum kind of loads in a little bit later. And it's probably not the best UX because we have some layout shift there that we could fix, but rendering that $200 minimum was actually requiring a couple network calls to a couple services that were slower. And just by moving that to render in a little bit lazily, we increased the number of actions that were less than 1 second by 12%. And so we said, hey, this is great. Let's lazily load anything, anywhere, as much as we can. So we tried this on our order details screen, and you can see in the upper corner here, the chat button loads in a little late, and there is also an upsell carousel that's slightly below the fold that you can't see. And those two things were the critical path streams, so we pushed them back to be lazy. And coincidentally, we found it almost the exact same 12% increase in actions, but we saw a 5% decrease in engagement with the screen. So when you think about what you're going to lazily load, really think about user experience. You want to make sure that the important information is there for the user. All right, next we can look at caching. So the general idea of caching is to eliminate duplicate work by storing the result in a locally more accessible, faster area. And the challenges you'll face when you start thinking about caching are what do you cache, how long do you cache it for, and how to know if the data in the cache is valid. You know, as the saying goes, there's only 2 hard things in computer science, cache invalidation and naming things. So when we started thinking about caching, we wanted to look at where can we get the most bang for our buck, and we started with the network. HTTP already has caching kind of built in. You can use the cache control header to indicate how responses can be cached. And so we looked particularly at max age and only if cached. Max age says how long can this value live in the cache and be possibly valid for. And only if cache says I want to grab the value directly from the cache, and if there's nothing in the cache, then throw an error. What this looks like in kind of a flow is you make your network request. If the cache isn't enabled, then you just make a normal request. If it is enabled, then you look for a previous response. If there's no previous response, again, just normal request. If there is a previous response, then we want to validate that with the server. And depending on our cache control or our conditional header, we may get like a 304 response, which would say, hey, use the cache data that you have. Otherwise, it'll just be like a normal network request. And you can see that outside branching path for the only if cached, where if the cache is enabled, we just grab something from the cache or we error out. The cool part about all this caching is it is also built directly into OKHTTP, so you don't have to do a lot of work. You pretty much just specify a cache size, create a cache object, and then add that onto your OKHTTP builder. Interesting thing to note with this cache is it's an LRU cache, and it only works on GET requests. So the main changes for this are you'll add this pretty quickly, and then your backend will have to add the cache control headers for the network requests, the network responses. So we also mentioned to check if there is a previous response and we have to validate with the server. So how do we know if we have how do we match items in the cache? One easy way to do this is with e-tags, which are essentially UUIDs, not quite, but they're unique identifiers that the backend can send down whenever you get a response, and then you can use a conditional header to pass that back up. So we use the if none match header most places, and basically that says, hey, I got a response, you gave me this tag for this resource, and I'm going to send it back. If you don't have that, then, or if it has been updated, send me a new response. Otherwise, I can use the response in my cache. And you'll notice that this still requires a network request to validate that. But because you're not doing like typical work on your server, we found it was pretty much about the same time as a ping. So on Wi-Fi, like 15 milliseconds compared to an actual network request. On top of network caching, you can also do any sort of local caching. And local caching can be done on disk, in files, or a database, which would enable offline support, unlike network caching. Or you can do it in memory. Anything you store in an object that is retained is technically a cache. And this is commonly done with like view models or remember functions in composables. At the base level, anytime you declare a variable and put something in it, you've cached that value for some lifetime. And so when it comes to data that you're caching, you really have to think about what is the lifetime? How long is this valid for? Is it for across app sessions, for an entire app session, an activity, fragment, view model, view? Is it within the scope of a function? And so when we think about data lifetimes, let's take a quick little detour to our dependency injection system. We use Hilt, and if you haven't used Hilt, it's a library on top of Dagger for dependency injection. And it simplifies a lot of the Dagger-related infrastructure by providing standardized components and scopes, where components and scopes kind of map to life cycles. From the official Hilt documentation, you can see this is the standard set of components. And for every component, it has access to objects in its parent or its ancestor component. So if you have an object in the view model component, you can access something in activity retained or singleton. And the scopes that we mostly focused on with our architecture are the singleton and the view model component. So singletons are pretty self-explanatory. They are singletons. They can be created as soon as application on create, and they stick around until the process is destroyed. View model components are created whenever there is a view model created event, and they stick around until the view model is destroyed. With these, you have to use the scoping annotation. Otherwise, you'll be creating a new instance each time you do the injection, even within that component. So if you have a view model scoped object that has the annotation, and you create it for a view model, it'll be a single instance for that entire view model. So where does this fit into caching? You might have seen this diagram for the repository pattern. And a repository is simply an object that is used to coordinate getting data from different data sources. This can be backed by network or disk, but the repository itself can be viewed as a cache on top of whether you're using network or disk data. And any data that you keep in the repository will stick around for as long as the repository exists. For our app, we can take a look here at our user repository, a little simplified, which is a singleton. And so we will have a single instance of this user repository for the lifetime of our app. When it is created, we'll load a user or when a user logs in, and we will only ever have 0 or 1 users logged in at a time. So we can use this behavior subject to hold data. If you're not familiar with Rx, a behavior subject will emit the last value that it has whenever there's a new subscriber without having to do any of the work upstream. So we load a user, we put it on the behavior subject, and anybody who subscribes will get that value that's already there. For our brand screen, we can create a view model scoped repository. And when this is initialized, we'll load our brand, most likely from the server, and put that into a similar behavior subject, so anybody who subscribes will get the latest value. When we move into our view model, we annotate this as a Hilt view model, which allows us to inject into this view model. And we pass in our user repository and our brand repository. Looking at the scoping levels, our user repository is a singleton, so we will have one object that then gets injected to both, or to as many brand details view models as we have. But for each brand details, we will have a separate repository, which makes this really easy to control the lifetime of the data. We create one, we pass in the ID that we want to load, and that response will stick around for as long as the view model sticks around. And then once the view model gets cleaned up, that data gets cleaned up and we free up memory. So the great part about caching is it makes things more accessible, it's faster to access, but caching only helps the second time you want to get data. So if you never hit your cache again, then it really didn't help much. And one thing you can do to avoid that is to prefetch data and preload your cache. And for this, you want to load data before it's needed. So if we look at this screenshot on the right, this little GIF, you can see that whenever somebody wants to go to their order details or their orders list screen, they first have to go to their profile screen. And order details are things that don't update very frequently. You change the shipping status maybe once a day. So it's prime data for getting high cache hits. And we also know that there's a high intent for a user to go to their order list when they get to their profile screen. So it's a perfect time to preload that data. By loading the data there, we do have to kind of think about the balance of unnecessary network calls versus the expected cache hits we're going to get, just because we don't want to use the user's battery or network data. So you can also just optimize this to run maybe when the user's on Wi-Fi. But by loading this data from the settings screen, we saw a 20% increase in actions that were happening under 1 second just for that. So that brings us to our last step, which is control. And I don't have a lot to share here because this is where we're working on right now. But the idea is that we want to find issues early. So we're starting to look into benchmarking tests. And if we do release issues, we want to make sure that we're alerted as soon as possible so we don't have poor user experience. To kind of wrap up this whole thing, the steps that we took were to define. So first, figure out what performance means, figure out what speed means, what you care about. Think about it from a user's perspective when you're defining which actions you want to improve, which areas of the app you want to optimize for. Next, you want to measure. You want to gather real user data, and you want to make instrumentation easy for your developers. Then you can analyze that data and find where the slow points are, whether that's loading your data, processing it, building your UI state, or drawing the screen. Then you can improve, and remember you're trying to eliminate duplicate work, wasted work, unnecessarily serial work, and non-blocking work that is blocking. And you can use techniques such as parallelizing and deduplicating network requests, lazy loading, and prefetching and caching. And finally, control. You want to try to prevent regressions early and be alerted whenever there are regressions so you can fix them and loop back to analyzing whatever the problem was that you caused. That is all I have.